Welcome to Almost Here, Round the Corner Future Technology podcast with Richard Jacobs. Future technologies poised to transform our lives for better or worse are the focus of this podcast. Almost here means these technologies are now here and starting to be used, or just around the corner, from Bitcoin to artificial intelligence, 3D printing, blockchain, virtual reality, and more.
Hello, this is Richard Jacobs with Future Tech Podcast. Today I have two interesting guests from a company called Fast.AI, Jeremy Howard and Rachel Thomas, founding researchers, they call themselves. How are you guys doing?
Hi there.
We're doing well.
Good. Welcome to the Future Tech Podcast. Thanks so much for coming. I appreciate it.
Thank you. It's great to be here.
Thank you, Rich.
Yeah, so for starters, I always find it's better to have the guest introduce themselves and tell what they do. I tend to screw it up. So, yeah, if you guys would, please let me know what Fast.AI does and what you guys do there.
Okay, Fast.AI is trying to make deep learning, which is a kind of area of AI where a ton of breakthroughs are happening right now, more accessible and easier to use. And so traditionally, a lot of materials in this field kind of assume you have a graduate level math background and are very exclusive. And we created a course, kind of a practical course for coders to kind of tear down that exclusiveness and make this field more accessible.
We also do research into foundational methods which can make it easier for more people to use this field. So we kind of iterate between doing the research and then teaching and back and forth like that.
Yeah, so all right, we'll get into deep learning and artificial intelligence in a minute, but let's start from a different angle. What makes it inaccessible to people and companies that would consider using it? Do they not even know what it's capable of? Do they just think it's like the movies and the Terminator? I mean, what are the stumbling blocks that your educational work and your smoothing the way helps do?
So there are a lot of stumbling blocks. One is that, and this is starting to change a little bit, but a lot of experts in the field weren't actually writing down or sharing the practical information you needed for a while. And so kind of people publish these theoretical papers that don't actually have the information you would need to implement this is one big issue.
Okay. I think, overall the issue is a level of exclusivity, which is totally unnecessary, but causes a lot of people I've spoken to at organizations to be kind of terrified of getting into this field. It seems like you need a Ph.D. from Stanford and 10 plus years of expertise, and that you can only have gone to one of a small number of exclusive institutions, and that you need millions of GPUs and a huge expensive cluster and petabytes of data. And all of this exclusivity is very self-serving, I think, to the people that have promoted this idea, but it's left a lot of organizations feeling like that this is possibly beyond them and that they wouldn't know even where to start. I think increasingly more and more organizations are aware that deep learning is something which could make a significant difference, and that's changed. About 2.5 years ago, I did a talk which ended up on TED.com, which introduced the potential of deep learning. And at that point, that was a key issue, was that people just didn't know this is a thing and that this is such a world-changing thing. In the last 2.5 years, I think things have changed so that now a lot of people are aware of the power of this, but they're not aware of how they could do it themselves.
Well, let's start gently. So what is, talk about what is artificial intelligence and then talk about deep learning specifically. What's different about it versus this umbrella term AI?
So deep learning is a very specific class of algorithms, also referred to as many-layered neural networks. Deep learning is typically applied to kind of very specific problems. Sometimes people talk about like artificial general intelligence, and this idea of kind of creating a computer that's a bit like a human, whereas in deep learning, that's kind of like using neural nets for a specific task. Like I want to be able to recognize pictures, or I want to be able to recognize speech and, write it in text.
So artificial intelligence is, one of these rather umbrella terms that is possibly so vague as to be meaningless. It refers to really anything that gets your computer to behave intelligently, under some definition of intelligently, and it covers a variety of techniques that have been around for 60 plus years. This particular approach that Rachel's talking about of using multi-layered neural networks, although it's been around for a long time, it's only been the last 5 or 6 years that it's really started producing state-of-the-art results. But what's really interesting about it is that it's fundamentally an exponential technology, which kind of means that the more time that goes on, it gets multiplicatively better. So since that time, 5 or 6 years ago, when it started achieving a handful of state-of-the-art results, it's improved multiplicatively every year since then, now reaching the point where it is exceeding human performance at some pretty human types of things, such as recognizing the contents of images or understanding spoken Chinese or English speech.
Okay, so what makes deep learning particularly suited to being a useful type of AI versus, just a neural network or, machine learning or these other buzzwords that people hear about?
It is just
how does it work?
So deep learning is a neural network which has got more than one hidden layer. So basically, neural networks have been around for many decades. It turns out that if you add more hidden layers, they become exponentially more powerful, and they require, as opposed to if you only have one, it turns out it requires exponentially more memory, which is a bad thing. So this increase in the number of layers in neural networks has had huge consequences. Basically, empirically, I think is the most compelling evidence here that not only are deep learning or deep neural networks the best approach for the vast majority of computer vision problems, most natural language processing problems, increasingly time series and structured data analysis problems. But as I mentioned before, furthermore, they're actually showing better than human performance in areas like understanding language and understanding pictures, which, there's never been a technology which has, just empirically achieved anything like these results before.
Yeah, so far it kind of seems like almost any problem it's applied to, it gets state-of-the-art results in. Which is really exciting.
Yeah, and so like if your organization is trying to do anything from, understand the gene expression in genome data you have through to figuring out how many cans of Coca-Cola you might need to sell at each of your stores next week, to trying to build a robot that can, or a self-driving car indeed, which can safely navigate an environment. These are all things where deep learning is likely to give you the best results, and also, interestingly, not require very much programming.
And I was just going to
let's talk about a specific use case. Let's talk about, I don't know, you go ahead and give me one. I can give you one, like, let's say I'm going to show you a series of pictures, and I want you to tell me if there's a cat in the picture. Let's talk about that, and then let's go into, like, another use case.
Sure.
If I wanted a machine to do that, for instance, or, how would it do it? How does the deep learning do it?
So a key thing you're doing is that you'll have you teach the machine what you want it to do by having a training set. So you kind of would have pictures of cats that are labeled cat that you're training the algorithm with. So the algorithm kind of learns what the best weights are it has a lot of different parameters that it's fitting. But by giving it examples, you're kind of saying what you want the output to be.
So basically, the way this works in practice is rather than programming a computer by telling it the rules that you need to recognize, so rather than saying this is what a cat looks like, instead you give it examples. So you say, here's 1,000 examples of cat pictures, here's 1,000 examples of dog pictures. And it's funny you mentioned this particular example because in our online course, this is actually the first thing people do is recognize dogs from cats. In practice, they have to write 6 lines of code, have one folder in their computer containing pictures of cats, one folder in their computer containing pictures of dogs, and then you press go and you wait about 3 or 4 seconds, and at the end of that you've got something you can feed a new image into, and it'll tell you with 98% accuracy whether it's a cat or a dog.
And I think I want to highlight just Jeremy saying that this is different from a rule-based system. So you're not having to come up with any facts about cats having fur or being a certain shape or size. You're really just giving an example.
In fact, that 6 lines of code I mentioned, you can use the exact 6 lines of code to recognize which images contain
you can see which
logos
type of fish has been caught. This is another problem of identifying illegal fishing.
Yeah, you could figure out what kind of disease a mole on somebody's skin is or whatever. They all would require basically the same 6 lines of code.
Well, how does the computer do that without having rules? How does it know? Let's take cats. So without telling it, a cat's supposed to have 2 eyes, and they're supposed to be spaced approximately this distance, and ears and paws and whiskers. How does the computer know from training data? What is it doing to figure it out?
What ends up happening is that so there are many layers to this network, and by seeing lots of examples, different layers learn to kind of recognize different aspects. And so often the first layer is just picking up edges and noticing there's an edge here, or this is kind of what a diagonal edge looks like. And then lower layers or higher layers are putting those together and can say, hey, this is a triangle. And then the kind of deepest layers will have things of being able to recognize, like, this is an eye or this is a spiral. So kind of you have this increasing complexity that's being recognized at different layers.
The way this is set up was originally heavily inspired by neuroscience. So the way our eyes work is there are certain types of sensors, rods and cones, and then there's a certain way that the information from those is combined. And when people looked at it, they realized that there are certain operations from linear algebra that, reasonably closely, somewhat closely replicate these ideas. And so basically what people originally did was to say, okay, well, let's try and construct something which is loosely inspired by what we can see in terms of this nerve connectivity in the brain, or neuron connectivity in the brain and the optic nerves. And so the idea of this as being a kind of a mathematical function is a little counterintuitive, because it's a mathematical function with hundreds of millions of weights in. So although it works exactly the same way as learning any other parameters in a function, it's at such a scale that, it's able to create this kind of hierarchy that Rachel described, where it can learn to recognize edges and combine them into corners, and then combine them into textures, and then combine that into recognizing fur, and then combine that into recognizing ears, and then combine that into recognizing heads. It's really, the scale of this is well beyond anything that we can kind of intuitively understand, and so it kind of manages to do things which at first glance seems surprising for something that is actually incredibly simple.
And there's actually a theorem decades ago that kind of anything could be represented with a neural network. But at that point, there wasn't the computational power for it to work in practice, or the quantity of data needed.
All right, let's continue with this example. So we show it pictures of cats, labeled cats. So you probably show it drawings of cats, and big fat ones and skinny ones, and ones with one ear, and I guess a range. Then you show it a new picture that's not labeled, and you ask it to identify if that is a cat or not. And you said you've gotten it to like 98% accuracy that it can recognize a cat, right?
Right. And, in practice, it's probably higher than that. I mean, the data sets that we work with, or everybody pretty much works with, are very noisy. So when we actually looked at the 2% that it was getting wrong, quite often it turned out that it had not been labeled correctly in the first place, or it didn't actually contain a cat or a dog, or that it was an advertisement for a cat that didn't actually contain a picture of a cat in it, or whatever.
Or it was kind of blurry and we couldn't even tell what it was.
Yeah.
Right. Gotcha. Okay.
And it's also important to note that you're not just showing the network cats, you're also showing it pictures of things that are not cats. And so in our example of cats and dogs, you're showing it both cats and dogs. But there's a huge competition where they show 1,000 different categories of images. But so it kind of needs to see what the alternatives are.
And so what you've been describing then is, like what happens after you've trained it. So after you've trained it, you have a model now that can recognize cats from dogs, say. The actual training, using the lines of code that we developed takes, 3 or 4 seconds. Then the next stage is to go out into the wild and use that. So you might, put that on your mobile phone and create a little app out of it. And now you can point your mobile phone's camera at something, and that once it's trained, it only takes about 0.02 seconds for it to recognize what something is. And so that's why this works really well for self-driving cars, for example. So increasingly, people are using exactly this approach in self-driving cars in order to figure out, are there any pedestrians around? Are there any trees that we're about to run into? Whereabouts is the middle of the road? And so forth, using basically exactly the same kind of approach that we just described.
How important is the positive training data versus the negative? Like, how do you know the mix of stuff that's necessary to tune the learning to the right degree of accuracy?
In practice, these things require a certain amount of experimentation, but they're not terribly sensitive. In general, if the data that you train with has a similar mix to the data that you're likely to see in the wild, that's likely to be a good rule of thumb.
Yeah, so except for exceptions where what you're looking for is incredibly rare. Mm-hmm. So if you have something like trying to identify credit card fraud and most credit card transactions are fine, you might want to show it a higher percentage of credit card fraud than exists in the wild.
Yeah, so for example, a couple of years ago, I started a company to do medical imaging diagnostics to try and so initially we tried to improve the ability to diagnose cancer early. Luckily, most people don't have lung cancer. So we grabbed, 1,000 examples of people that did have cancer and 5,000 examples of people that didn't have cancer. Because we wanted to make sure we had enough examples of cancer that the system could learn what it looked like.
And this was using CT scans, so images.
Right. Okay. Sure. So, that's interesting. So let's talk about the cancer example. What was the accuracy of it finding cancer versus what was the accuracy of it? What was the accuracy of the false positive versus the false negative? That's my question.
Sure. So, you can always tune that to any kind of combination you want because it returns a probability. So what we did was we calibrated it and compared it to a panel of 4 human radiologists. And what we found was that, not surprisingly, the human radiologists prefer to be conservative. So they had a 7% false negative rate, so they missed the cancer 7% of the time. We didn't have any false negatives in our sample, comparative sample. And then for false positives, I can't remember the exact numbers, but basically it was very, very high for the humans, like over half, I think, were false positives. And really? I think we were like 50% better or something. Like we certainly our false positives were a lot rarer, which meant if you used a system like that, not only would you have less people with cancer failing to be noticed, you would also have a lot less unnecessary biopsies. But much more importantly, the computer can do it in well under a second, whereas a human takes 10 to 15 minutes. And there's a huge shortage of doctors in the world, in the developing world in particular. There's a 10x to 20x shortage. So this kind of technology, could save millions of lives.
And often these systems would be used together with a human. And so you could have a computer kind of flagging, like, these are the ones we definitely want to show to the human radiologist, which allows the human radiologist to kind of work much more quickly when they're working in partnership with a diagnostic system.
Yeah, so once you trust the AI system, it gives you a confidence level, a probability, right? So the ones that aren't absolute, I guess the lower confidence levels would be given to a human to double check, right?
Right. And also, perhaps more importantly, it points out the areas which may have issues. So it allows the human to focus in on the interesting parts of the image. The reason it takes 10 to 15 minutes is it just takes a really long time to study every part of every slice of a CT scan. So if a computer can kind of let you know, these are the 3 bits that you're likely to be interested in, that's going to save a lot of time and also make them more accurate.
That's very interesting. Okay. So what do you see are the stumbling blocks? You talked about people being terrified at one point. Do you approach industry or does industry come to you and say, hey, we heard about this deep learning stuff. Do you think it'll work for our application? Or does both happen? And And when it happens, what are the fears that companies and people have about employing a system like this?
So we kind of, because we're just small, we have to take more of an approach of people come to us, and not only do people come to us, but people come to, the online course that we have created. We don't have time to do really any consulting. So people seem to find us. There's over 50,000 people have started the course already.
Wow. And
then we have these forums where these people then talk to us and to each other about what kinds of things they're working on. So we know that people who have been through the course have done everything from analyzing the noises heard in rainforests to find examples of illegal logging, through to tracking mouse movements in, huge kind of anti-fraud systems to try and predict fraudsters, through to trying to improve the accuracy and performance of radiology in Africa, and so forth. So people kind of, so people hear about us one way or another. They do the course. They see dozens of examples of the results in a wide variety of areas. And we're constantly then kind of telling our students, like, this week you should try to, apply this to a project that you're interested in or you have access to, and try and use these kinds of techniques. But during the course, people end up, building a lot of cool stuff. And then after the course, people tend to stick around in this forum community and keep on telling us about what they're doing and asking for help and giving others help. So it's kind of trying to create a really high leverage approach by having every student that's gone through this course effectively become part of a peers helping peers community.
And one message we're still trying to get out to companies. I would just say a lot of companies still think that they need to hire a Stanford PhD to be able to do this. And so we're really trying to get the message out there that they can train the smart employees they already have to be able to do this.
I mean, not only can they, but probably they should.
It's easier.
Because, if you hire some computer science or math PhD straight out of university, they're not going to understand very much about the mechanics of, selling cans of soda or, saving rainforests or indeed, identifying lung cancer. Whereas the people who are inside your organization are there because they do know a lot about this stuff. And so it's, we found it's actually much easier to teach the domain experts how to use deep learning as a tool than it is to teach people that already understand deep learning how to kind of have that deep, nuanced understanding of the kind of strategy inside some domain, so that they actually recognize what problems to solve and how to make kind of thoughtful decisions and compromises and so forth.
Tell me more about the course. Does it cost? How much does it cost? How long is it? Do you have different levels, or is it just one course?
So the course is completely free, and it's available at course.Fast.AI. And it came out of, we taught an in-person course at the University of San Francisco's Data Institute, and that was taught in person to 100 students, and we recorded everything and put it online. And the part one of the course was a 7-week evening course with the expectation that students would spend about 10 hours a week on it, so 70 hours total. And then we just finished teaching of part two of the in-person, and we're going to release that online soon.
And so part one describes itself as practical deep learning for coders. So it assumes that everybody who takes it has had at least 1 year of coding experience. And the idea is that by the end of it, you're going to understand all of the current best practices in the areas for which deep learning is a reasonably mature technology. Part two, which we've finished recording and we're just working on getting it online now, on the other hand, is the cutting edge deep learning research for coders. And so this is for people who have finished part one and want to go to the next level of understanding the most recent research papers and perhaps working on fairly novel problems. As Rachel said, it doesn't cost anything because for us this is entirely it's a mission for us. We basically think that this has the potential to, and in fact, we know now from the results of our early students that this is having a hugely positive impact on the world when people who, are all over the world are actually taking this and making a difference by using this technology. So one example that I'm really fond of is a fellow in India who has used this to build a system that can help farmers in India basically with their insurance claims by using deep learning to analyze all of the satellite imagery of India. So there have been 5,000 Indian farmers every year commit suicide because of this problem. And this guy,
and the problem is that they're taking these very predatory loans from kind of loan sharks that then threaten them with violence and harass their families, but they're not able to qualify for better loans because they can't prove how much land they own or what type of crops they're growing.
Yeah. So, this is something that Rachel or I would never know this was a problem or how to solve it. But one of our students is right in the middle of all of that. And so he immediately recognized that this kind of technology would be very helpful here, and he's started doing it. And
he was part of our international fellowship program. So with the in-person version, we had both diversity fellowships and international fellowships because we really wanted to broaden the scope of who's doing deep learning.
What are some of the, you talked about this application, which is interesting and unusual. What's the some of the most unusual applications of deep learning you've seen or impactful? What do you think? You talked about identifying cancer, which is tremendous, and land rights in India. But anything else that's like strange or amazing to you that just blows you away that it's possible that it can be done?
One of our students is a natural language researcher in Pakistan, and Pakistan has 70 spoken languages, and none of them have that many resources. And as part of our course, he put together the largest corpus of Urdu text that's been assembled and trained word embeddings on that. And that'll be a really helpful resource for anyone studying Urdu or trying to translate other materials into or out of the language.
In fact, this approach has already been widely used in the English language. Whenever you use Google Translate, you're basically using that kind of system. The Chinese company Baidu has a speech recognition system that can recognize both English and Mandarin speech more accurately than humans can. So with this kind of approach now, this is the kind of thing which can allow folks that speak Urdu in Pakistan to also use this technology. I think overall the most impactful areas that I'm aware of, I think medicine is the most impactful area. There's a hospital in Los Angeles, for example, that actually has data scientists go on rounds with doctors every morning, and they've been using deep learning to predict the mortality of every patient in order to understand which patients need a higher level of medical care. And that kind of thing's a fantastic example.
Yeah, in our course, we had several Alzheimer's researchers that were taking the course. I know that's being applied to Alzheimer's. We also had someone that was working on, I think, a wearable device for Parkinson's patients to help their doctors better monitor the progress of their disease.
Yeah, so I think overall medicine would be one of the most socially impactful areas. Financially, though, obviously, self-driving cars is hugely important. There's plenty of people using this for, the very high value area of kind of equity trading and hedge funds and bonds and so forth.
And this also just reminds me, a lot of our students, particularly kind of those in other countries or working on more obscure applications, don't have access to, these huge computation centers or servers with tons of GPUs. And so both in our research and in our teaching, we're really interested in ways to best leverage this technology for people with few resources. So we're interested in people who have small data sets, who can't afford much GPU time. So that's a real area of focus for us that's not necessarily an area of focus kind of for the rest of deep learning.
I have a question that'll probably stump you because I've never gotten an answer to it. How much training data is enough for a given application? And are there formulas you can use to get you to a certain confidence level? Like everyone tells me, oh, you just need a lot of it. Well, what's a lot of it? How do you know?
Yeah, so, it's both very easy and a very hard question. It's very easy because there's some level of model performance which is going to do what you need to do. So if you need something that's capable of safely driving a car, or something which can recognize tumors better than doctors, or whatever, there's some benchmark level. And so it's actually very easy just to take whatever data you currently have and train a model and see if it's good enough. And if it's not, you can actually extrapolate very easily. You can try using half of that data, and then a quarter of that data, and then a tenth of that data, and you can basically extrapolate the curve of performance versus amount of data, and then that tells you exactly, well, very close to exactly, how much data you'll need to get the performance that you need. The good news is that with deep learning nowadays, often you don't need very much data because of something called transfer learning, which is becoming increasingly important, which is basically, it turns out that you can use a model that's been trained on a fairly different problem, and basically take that model and use it as the starting point for training your model. And it often means that you need orders of magnitude less data, and you also get much fewer errors. So with transfer learning, often it's not actually about how much data do I need, but are there other cheap to find and access data sources that I could use to create a starting point model for transfer learning?
The other technique that's often used, Jeremy mentioned this earlier, is data augmentation. And that's where you can often kind of alter your data to make more. So like with the pictures of cats example, you can take a picture of a cat that you have and crop it in different ways, zoom in, rotate it vertically, apply a little bit of a color tint. And by doing things like that, you're kind of multiplying the amount of data you have, because it'll still look like a cat as long as you're altering it in a way that's reasonable for how cats look.
So, in general, as a rule of thumb, we tell people if they have less than, 100 or 150 items, probably they're not going to have any luck with deep learning at all. Once you've got at least that amount, depending on your ability to use transfer learning and data augmentation, and of course the complexity of the problem you're trying to solve, then you may well be in a position to get good results.
But you typically don't need millions of data points, do you?
Oh, certainly not. No, not in general. Unless you're working on a type of data that is totally, totally different to anything that anybody's worked on before.
Okay. So people can take your course, they can ask questions, they can get help with projects. What if they get stuck? What are some other resources they can use, or code bases, or other ways to get themselves to a point where they can start solving their problems if they get stuck?
Yeah, so by far the best resource is the forums that we have, which is at forums.Fast.AI. Actually, regardless of whether you're using the course, anybody can use them, and they're extremely popular. So pretty much any time a question gets asked, it gets answered often within a few minutes. It's also great for people to try and answer questions themselves, because it really gets them, even if they're not quite sure of their answer, they can make a start, and then somebody else will help by correcting pieces that aren't quite right.
We're also really encouraging people to start study groups in their area. And so we know of several companies where teams have started working through the course together and have regular meetings. And people will often post in the forums, I live in such and such city. Is there anyone else in this city who is taking this course and interested in studying together?
Yeah, so when we announced that we were going to be doing the in-person part 2 of the course, it turned out that there were these kind of lunchtime study sessions at Apple, at Airbnb, at Uber, and so forth, where those folks basically went, oh, that sounds great, and then they kind of came together to our in-person course. We're also aware of people that have formed groups everywhere from parts of India to parts of Africa. We're obviously less familiar with those kinds of remote examples, but it does seem like we meet somebody every week who says that they're part of a company or geographic group of people that are working through our course together.
You don't have an AI chatbot that runs the forum, do you?
No.
I'm just teasing you. I'm teasing you.
I got to say, of all of the overhyped technologies, chatbots would have to be towards the top.
Oh yeah, I'm
not
sure.
one that we're big fans of.
Yeah, I know we hate them too. I hate them too. All right, last couple questions. So you've got the course. You're working on another course. What else does Fast.AI have? You have the forum. What else do you guys do as a company that you think is valuable to the to the AI community and to businesses?
And this is something else, kind of as a side thing. We do a fair amount of writing on our blog about data science. So we are kind of putting essays out there. I have an Ask a Data Scientist advice column there. This is all at Fast.AI.
Then the other thing that's going to be, it hasn't really happened yet, but there's going to be a lot more of, is the next stage of research, where we'll be taking all of the things which we've learned after teaching these two parts of the course and using them to create better tools. So I'm helping to launch a company which will be trying to improve the ability of humans and deep learning systems to work together through visualization techniques. I'm starting to work on the largest lung cancer data set that's been used in this kind of area to try and come up with even better diagnostic tools. We're also going to be looking to continue to simplify the libraries and systems so that the next time we do this course, hopefully we can teach twice as much in half the time to people with half the amount of expertise and experience.
Yeah, our goal is, whenever teaching, to kind of find the things that are most painful or hardest to learn. And then when we return to our research, see if we can write better libraries and better tools so that the next time we teach it, it'll be easier.
Or find those areas which maybe it didn't quite suit as well. So, for example, we actually discovered that deep learning can create state-of-the-art results in time series analysis and in structured data analysis. These are perhaps the two most important areas for regular corporations. But it turned out that there's no libraries whatsoever to make that remotely easy. So that's like a key area that we're going to be wanting to do research into figuring out how to make that dramatically easier.
Very few people are applying deep learning to time series right now, and there's a lot of opportunity there.
What does that mean, time series data? Like, what's an example?
Sales. Oh.
Yeah, sales.
I would say so sales data. So anything where you have, like daily sales or profits.
Number of people that are going to your hotels, or the measurements that you're getting from the sensors inside your oil wells as you drill.
Oh, wow.
Or basically any kind of IoT sensor would be a time series. Any kind of corporate financial indicators will be time series. Any of the kinds of technical indicators that are used in hedge funds are all time series. So
okay, that makes sense.
Also in medicine, ECGs or electronic medical records, they're all time series as well.
Okay, well, very good. Last question I have, and this is just for my own curiosity. I've heard that AI systems sometimes will produce results and you don't understand how it did it. It has its own literal machine intelligence. There'll be emergent things that come from the AI that were unexpected. Do you have any examples of that? Anything that was like, whoa, that's pretty cool?
Oh yeah, I mean the lung cancer example I gave was exactly like that. There was 4 of us on that team. None of us had any medical background at all, and we were like, whoa, this thing is diagnosing cancer better than top radiologists. We had no idea how it was doing it. But it turns out that increasingly in the last couple of years, it's not invested in enough, but people are starting to invest in building the tools and systems that allow us to basically ask a neural network what it's doing and how it's doing it. And so we are starting to find some systems emerging that are actually allowing us to use deep learning not just to solve predictive problems, but also to actually understand the kind of causal systems going on behind those problems.
Okay, well, very good. I know I kept you guys long. I apologize for that, but there's a lot to talk about with this topic. Yeah. So, last question is, how can it's probably obvious, but how can people get involved and find your course and get to the forum? Just go to the website, or?
Definitely, yeah. So the course is at course.fast.ai. Our forums are at forums.fast.ai, and then our writing is at fast.ai.
Yeah, and I would just really encourage people to join the forums and, say hi and ask the question, and suddenly you'll find you're part of a global deep learning community, and you'll never look back.
That's great. Well, Jeremy and Rachel, I really appreciate you coming and being guests on the podcast, and, thanks so much for your time.
Thanks for having us.
Yeah, thank you.
You have been listening to Almost Here, Around the Corner Future Technology podcast with Richard Jacobs. Subscribe to this podcast, post a review to discover more future technologies that are poised to transform our lives for better or worse, such as Bitcoin, artificial intelligence, 3D printing, blockchain, virtual reality, and more.